Welcome back, students. In this video, we're going to look at an introduction to radicals. First, let's talk about how radicals are formed, and then I'll show you exactly what a radical is. There are two types of bond cleavage. The one that you're used to is called heterolytic bond cleavage. And if you think about the prefixes hetero and homo, homo is going to mean the same and hetero is going to mean different. So what would be the same or different when we're talking about a bond breaking? What happens in heterolytic bond cleavage is that the bond, which is made up of two electrons, breaks in such a way that both electrons go to one of the atoms involved in that bond. What happens then is you end up forming ions, because in this case, X will have extra electrons, Y will have a lack of electrons, so X will be negative and Y will be positive. This is a heterolytic bond breakage because two electrons are going to one of the entities that form or were involved in that initial bond. Homolytic bond cleavage looks different than this. In homolytic bond cleavage, one electron from the bond is going to go to the X, and the other electron in the bond is going to go to the Y. When we draw this, our arrows are going to change. What I mean by that is instead of a full arrowhead like we saw over here for heterolytic bond cleavage, which describes the movement of two electrons, now we're going to use this fishhook arrowhead, where that describes the movement of one electron. So this arrow is saying one electron in that bond is going to X, and then I'm going to draw another arrow saying the other electron in that bond is going to Y. And I'm just going to lengthen that bond a little bit so it looks a little nicer. So homolytic bond cleavage is going to give you X with one unpaired electron and Y with one unpaired electron. These entities where you have an unpaired electron, those are called radicals. And you might be able to imagine that radicals are not very stable. And so what they do is they react with anything that they can get in contact with so that they can reach that point of greater stability. And we're going to talk about that in a later video. Let's talk about the structure of radicals so that we can utilize this to help us figure out stereochemistry for future reactions. Radicals are going to have a structure that's partway between a carbanion and a carbocation. Well, that makes sense, right? If a carbanion has two electrons and a carbocation has a lack of electrons, so no electron pairs, then the radical is in between that, right, with one electron. So let's remind ourselves what a carbocation and a carbanion structure look like. If we're looking at a carbon, I'm going to draw a dot right here, and that's going to symbolize my carbon. For carbocations, this carbon is sp2 hybridized. That means that this thing is your empty p orbital. And all of the bonds around that carbon are in the same plane, and that plane is drawn here. So that's kind of like the plane of the ground, showing you that the empty p orbital is perpendicular to that. That empty p orbital has a lack of electrons, and that's why you have a carbocation here. Whereas your carbanion is a little bit different. It is sp3 hybridized, which is why the shape of this orbital looks different, because this is an sp3 hybrid orbital that the lone pair is living in. So I've drawn the lone pair in the orange lobe. The dot that I'm going to draw in here is the middle where your carbon would be. And this is your sp3 hybrid orbital. And it contains a lone pair. Now, because you have something that's sp3 hybridized, you now have a different shape. Right? Instead of trigonal planar like you had over here, this is now going to be trigonal pyramidal. What that means is we have a different bond angle. And the atoms that are connected to this sp3 hybridized carbon, which I haven't even drawn, are going to be not all in the same plane, but kind of slightly downward, or they could be slightly upward. So then what is the structure of a radical if it's not a carbanion and it's not a carbocation? And the answer is you would just kind of mentally meld these. But that can be hard to do. So a lot of times what we do is just kind of imagine your carbocation for your radical structure, because it's easier that way. And there's two different thought processes as to like what's really happening with the structure of your radical. And so instead of explaining what those two different thought processes are, what we can do is just imagine that your radical structure looks a lot like the carbocation structure, just mentally add a singular electron to that. And that's going to help us explain the stereochemistry for our future reactions. Just like carbocations increased in stability when we added more alkyl groups to them, radicals are going to do the same. So if we start at something that's a methyl radical and we go to a tertiary radical, what we see is stability increases as we add these alkyl groups. So here we have an alkyl group, here we have 2 alkyl groups, and here we have 3 alkyl groups. Right, we call this one methyl, this one was primary, this one is secondary, and this one's tertiary, just like how for carbocations, instead of having that radical, that lonely electron that I'm highlighting in yellow, you had a lack of electrons there, so you had a positive charge when you were trying to classify your carbocations. And just like carbocations, you now see that as we add alkyl groups, those alkyl groups are doing the same kind of thing that they did with carbocations, where they're donating a little bit of electron density to that not completely filled orbital. And as you have more alkyl groups donating just a little bit, you increase that stability. And similar to carbocations, benzylic and allylic are even more stable. So let's look at those next. When we start considering benzylic and allylic, we need to look at the arrows of how we're going to generate the subsequent resonance structures. I'm going to do the allylic one here for you, and then I want you to watch the next video where we talk about arrow pushing patterns. Then I want you to try the benzylic one on your own when you're ready. And when you get worried that who am I going to compare with, you don't have to worry about that. Just Google search benzylic radical resonance structures and you'll find the figure. And it's also in any textbook, so you'll be able to find it. Let's go ahead and do the allylic one. When we're looking at resonance structures here and drawing this for radicals, remember we're using fishhook arrows. When we're utilizing those fishhook arrows, they're describing the movement of one electron. Now, because you've seen allylic carbocations and allylic carbanions, you already know what the allylic resonance structure for this is supposed to be. So let's cheat a little bit, because the difficult part is generating the other resonance structure, not figuring out what it is, at least in this example. So it'll follow that same pattern that we've done before, where we're kind of seeing that flip-flop. Mind you, right, there actually is no flip-flopping, right? We're just trying to draw on paper what actually exists in real life. Now we want to draw the arrows to show how you get that other resonance structure, because eventually you're going to get to the point where you use the arrows to generate the subsequent resonance structure. Now, those fishhook arrows are hard to do. So let's look at this piecewise. First thing I notice is I have a lonely electron here. That means that my pi bond needs to break and one of the electrons needs to go on that end carbon. So let's go ahead and draw the pi bond breaking and one electron going on that end carbon. The other thing I notice is that we have the formation of a pi bond here. That formation of a pi bond, remember bonds are made up of 2 electrons. We've drawn 1 electron going to where I highlighted in yellow, but there is another electron in this bond here that I'm pointing to with this arrow that I will erase in a moment. So we need another fishhook arrow starting at that bond. Where is that going to go? Well, we're trying to form a pi bond here, so let's draw it pointing in between the 2 carbons, right? So we're not pointing to an atom in this case, we're pointing to a pre-existing bond to say this electron is going to form another bond over here. So if you're pointing to an atom, you're saying put lone pair, well, no, not lone pair, lone radical here. If you're drawing a fishhook arrow between 2 atoms, then you're saying this 1 electron is going to be involved in making a new bond here. But bonds are made up of 2 electrons, so we need to have this electron also come over and together form that pi bond. So 2 things. First, we need brackets because that's a thing in resonance structures. Second is a lot of times students will get worried when I start my arrow tails up here and say that the pi bond is breaking, because they're like, but wait, the pi bond's on the bottom. Yeah, nobody actually really cares about that, right? It doesn't matter where I drew that second bond. We're just saying that one of those bonds is the pi bond and it's going to break. So don't worry about where you're starting that arrow as long as it is in the middle of 2 atoms where there's a pi bond. Once you feel like you've had the hang of some arrow pushing, what I want you to do is give the arrow pushing for the benzylic one a try. It is going to have quite a few more resonance structures than this one, so be mentally prepared for that. Let's wrap up. In this video, we talked about radicals. We looked at homolytic and heterolytic bond cleavage, and we considered the structure of a radical, which was technically partway between a carbocation and a carbanion, but for our purposes, it's probably just easier to imagine a carbocation with 1 electron. Then we also noticed that the stability of our radicals matches that of carbocations. So as we see more R groups attached to the carbon that bears the radical, we're going to see an increase in stability. And just like how carbanions and carbocations were stabilized by resonance, the same is going to be true for radicals. So allylic and benzylic radicals are quite stable. Thanks so much for watching. This is Katoni signing out.